In this video, we'll summarize the methods for curve fitting and interpolation that we've discussed from the Methods textbook, Chapter 5. Curve fitting using linear least squares regression works for lines, polynomials, trigonometric polynomials, and in fact any function that can be transformed to a linear form of the unknown coefficients alpha. It works for all functions f of alpha and x such that this function is linear in the alpha. When we have functions that are nonlinear in the coefficients, then we can use nonlinear least squares regression, and we talked about doing this using the Gauss-Newton method. We introduced interpolation using both the Lagrange and Newton interpolating polynomials, using polynomial splines, and using the Fourier transform and inverse transform to arrive at trigonometric polynomials. Consider the data in problem 52 from the Methods textbook, Chapter 5. This data is represented by 10 data points that are plotted here with 4 different results from linear least squares regression of polynomials. We can fit these data with a line, with a quadratic equation, with a cubic equation, or with a fourth order fit. We might ask the question, which of these fits is best? And we can get some idea of that by looking at the magnitudes of the residuals. The residuals of the data points and each of the models are plotted here. And you can see that the line has the largest magnitude of the residuals shown in the open circles. As we add terms to the polynomial, moving from the quadratic to the fourth order, the residuals get smaller. That is, they get closer to 0. This indicates that the higher order polynomials capture more of the variation in the data. We can compare these using objective measures of the goodness of fit, such as r squared or r bar squared. As we increase the number of terms in the polynomial, not surprisingly, r squared increases. Remember that r squared answers the question, what fraction of the variation in the data is described by the model? Obviously, as the residuals are getting smaller, for higher order polynomials, we capture more of the variation in the data with the model. In fact, we can expect that if we continue to add coefficients to the model, r squared will approach 1 at the point where all of the data are exactly captured by the model. In this case, it's inappropriate to compare the goodness of fit using r squared because these models have different numbers of coefficients. Instead, we should use the adjusted r squared, or r bar squared. And in this example, r bar squared also increases as we add coefficients to the model. So we can say that the fourth order polynomial is a better fit than any of the other polynomials, because it has the largest value of r bar squared. While these polynomials may be suitable for describing the variation in the data, you would not want to use any of these for extrapolation, because the polynomials are all unbounded. That is, their magnitudes go to infinity as the independent variable goes to either plus or minus infinity. These functions are also not very good for interpolation, because they don't match the data points very well. For example, if we were to attempt to use the cubic polynomial to interpolate in this region, we would not do a very good job, because the cubic polynomial fails to capture anything close to this data point at x equals 8. If we want to do any kind of interpolation, we should probably use a different method. For example, we could use the Lagrange method to develop a Lagrange interpolating polynomial. Because we have 10 data points here, the Lagrange interpolating polynomial is a 9th order polynomial, but it exactly matches all of the data points. This may be more suitable for interpolation, particularly at intermediate values of the independent variable. However, at values of the independent variable near our endpoints, we can see that our interpolating polynomial does not do a very good job. We would not want to use this interpolating polynomial at x equals 1.2 or at x equals 9.8, for example. This type of wild behavior near the endpoints is common for polynomials that are designed to exactly match all of the data points. The Newton interpolating polynomial doesn't do any better because the Newton and Lagrange interpolating polynomials are exactly the same thing. They're just different ways at arriving at the same polynomial. As you can see here, these two polynomials are exactly the same. Instead, we might use a spline interpolation. Here we've plotted the nearest neighbor spline which is a series of step functions, the linear spline, which is a series of straight line segments connecting neighboring data points, and two different cubic splines, one using the not-a-not boundary condition and one using the clamped boundary condition, where the clamped boundary condition imposes a zero derivative at each of the endpoints. Finally, we might fit these data with trigonometric polynomials. If we do this using a trigonometric polynomial that has fewer unknown coefficients than we have data points, then we're performing polynomial regression, fitting the data to a sum of a number of sine and cosine functions. The third order trigonometric polynomial shown here fits the data points to the sum of 3 sine functions and 3 cosine functions. Comparing the polynomial fits to the trigonometric polynomial fits, you can see that this bounded oscillatory data might be better fit by sums of sine and cosine functions than by polynomials with similar numbers of unknown coefficients.